So we're now in the IntelliJ project for my EX35 example, which is in my Java 8 folder in my live lessons repository on GitHub. And this example is going to demonstrate how the flatMap operation doesn't scale when used with Java parallel streams. And then we're going to talk about how a combination of map, reduce, and Stream.concat can fix this problem. Let me ask a question. Can you see this, or is it too small? It's OK. OK, good. So let's go ahead and take a look at the structure of the code. There's a couple of constants we define here, and you'll see how these get used. There's a method later called check inner stream thread IDs, which returns one of these three values under different circumstances. And then we use things like filter and basically some other terminal operations in order to make sense of the results. So I'll come back to that in a second. Here's the main program. When we run the program, it tells how many processor cores we have available. This Mac has 10 processor cores. A little bit of interesting trivia. Macs don't have hyper-threaded cores. Unlike Intel has hyper-threaded cores. So if you have 8 cores, you have 16 hyper-threaded cores. Not that that always makes much of a difference, mind you. But for some reason, Macs don't have hyper-threaded cores, so the number of cores you have is really the number of cores. So we're going to run 2 tests. One is going to be the flatMap test, and the other is going to be the test for reduce and concat. Then we're going to print the results. And we're going to look at this from a couple points of view. One thing we're going to look at is the time taken to run the 2 tests. And you'll see, based on the time, that the version that's the flatMap version is much slower while it's doing the same computation. That's because it's not running in parallel. Here's the run test method. Run test takes the test we want to run and the name of the test. It runs the garbage collector, so everybody starts with a level playing field where we've got everything squirreled away and all the memory is available. And then we run the test using this clever little timer class I've written. And this basically starts the timer, runs the test, stops the timer, and then stores the test results into a map for later manipulation. So let's go take a look at the 2 tests. So here's the first one. This is test flatMap. And what this does is it's going to generate an outer stream. We'll look at how that works in a second. And then it's going to apply the flatMap intermediate operation, passing in an inner stream method reference. And as you'll see, this doesn't work very well because it doesn't run in parallel, even though we're going to tell it to run in parallel. And then it's going to go ahead and check to see whether all the results that came back from inner stream are sequential or not. And that's going to dictate the semantics of whether things ran in parallel or sequentially. And we'll take a look at this very clever little algorithm I wrote to do that. And when we're done, we'll see that this version will, in fact, run sequentially. Test reduce is going to do more or less the same thing. It's going to generate an outer stream that runs in parallel. We'll look at that in a second. It's going to then go ahead and map with the inner stream. And notice that when we use map for inner stream, we get a stream of integers. Whereas up here, for flatMap, we got a stream of integers because it flat mapped it. So now we've got this kind of quirky stream of integers. But then we use the reduce terminal operation in conjunction with Stream.concat. And that does effectively the same thing that flatMap was doing. It concatenates the streams together so we have a single stream. And so we have a stream of integers. And if for some reason things were empty, which they won't be, we just have a little thing here that says just make an empty stream. That's just there for syntactic reasons. So we end up with a stream of integers, and then we check to see whether all the results from that processing were sequential or parallel. And as you'll see, they will be parallel because this is a parallel stream version because the combination of map and reduce with Stream.concat obeys or honors the parallel directive. So let's go take a look at generate outer stream. What this does is it generates a stream of ints from 1 to outer count, whatever that may be, 10, 100, 1,000, whatever we give it. It's set by an option that we can provide on the command line. And that will then convert each int into an integer. We say, I want this whole thing to run in parallel, so all these things will run in different threads. I'll show you how that works in a second. And then just to prove that things are in fact running in different threads, we use the peek intermediate operation, which is just a debugging operation in streams. And it has a side effect, but it doesn't actually modify the stream at all. So what it's going to do is just going to go ahead and display the current iteration, in other words, 1 to outer count, and the current thread ID. And that'll tell us which threads are being used for this. Okay, so what we think about this is basically a glorified for loop using functional features to loop through a range in parallel. The inner stream method, this is the interesting one. This is the one that's either called from flatMap or from map. And what it does, it records the current thread ID. Whoever the thread is that this thing is running, we're going to take a snapshot, and we're going to say that's the outer thread ID. And then we're going to make ourselves a new atomic integer. You'll see what that gets used for in a second. We call that inner thread ID counter. And it's going to keep track of the number of integers that each inner thread is going to be processed on. We then make ourselves a new concurrent hash map that will associate the inner thread IDs with the number of integers processed by that thread. And then we generate another range. So this is from 1 to inner count. And the way inner count works is that inner count here is going to be coming essentially from the outer count. So it's going to be, let's say we have 10 items in our outer stream. So 1, the inner count would first be 1. The second one would be 2, then 3, then 4. So it's basically going through and essentially generating integers from 1 to outer count 1 at a time. So think of it sort of like a nested for loop kind of thing. But again, using functional features so we can make them parallel quite easily. And then what we do is we basically don't do much of anything in this method other than call this helper method called check inner stream thread IDs. And we pass the inner count, which goes from 1 to inner count. And that's basically saying where the end is. We pass in the inner thread ID counter, which is this atomic integer for reasons you'll see in a second. We pass in the thread map, which is going to map the thread ID to the atomic integer that corresponds to it. And then we pass in the outer thread ID, and that's there just for diagnostic purposes. And we'll take a look at what check inner stream thread IDs does. That's the meat, that's the key thing in this whole program. And what we're going to get back is going to be a value that'll either be S intermediate result, S sequential result, or S parallel result. If we get back an S intermediate result, we don't care about that value for the purposes of our test, so we're going to get rid of it. So as you'll see, S intermediate result has the value of 0. Doesn't really matter what its value is, but we're going to check to make sure that the value that comes back here is greater than 0, and we only allow things whose values are greater than 0. And the reason we do that is because we only care about sequential and parallel results, and their values are 1 and 2. Okay, so let's go take a look at check inner stream thread IDs. This is a really, really cool method. It took me a while to figure out how to do this, and it's pretty clever. So this method determines and prints how many threads are being used to process an inner stream. And if the inner stream is running sequentially, as is the case when flatMap is what's calling it, then the thread ID of the inner thread will be the same as the thread ID of the outer thread, because it's not running in parallel. Conversely, if the inner stream is running in parallel, then its thread ID may not match the outer thread ID. And that's because it's probably running on another thread. And you'll see there's some subtlety here, but we account for that in the implementation. So here's what it does. The first thing we do is we come in here and we use a very cool atomic check then act method on concurrent hash map. And what this does is it checks to see if the current thread ID at this point is already in the map. And if it's not, then we're going to make a new atomic integer and stick it in the map with the value 1. So what we're saying here basically is this thread ID has been encountered once at this point. And so we use an atomic integer because it's got cool reference semantics. So the map now has an atomic integer with a count of 1 for whatever the inner thread ID's value is, which might be the same as the outer thread ID or might not be. If what we get back from put if absent is not null, that means this is not the first time in. So in that case, we go ahead and increment the value, the count of the atomic reference, atomic integer that's in the map. And that's to indicate this is the next time that the same thread ID has been encountered. Now, if you get a count of, well, you'll see what's going to happen here in a second. Now, the next thing we do is we come down here and we check to see if the inner thread ID counter, when incremented and read, equals max iterations. Max iterations is the count that we pass in up here, which is going to be inner count. So inner count is what's passed there. So basically what that's saying, in not so many words, is this the last element in this range? And if it is the last element in this range, we're going to do some interesting computations. We're going to come in and we're going to ask our question. We're going to say, does the thread map have a size that equals 1? And if it does have only one element in it, is the element the outer thread ID value? And if that's true, if there's only one element and it's the outer thread ID, that means that the inner stream was running in the same thread as the outer stream. So this probably means it's sequential. And then we print out some diagnostics to indicate whether we think it was sequential or parallel. And then we return whether we thought it was sequential or parallel. OK, so that's kind of how everything works. So now let's run the program, and we'll see the behavior. And we'll run it a couple times. First time we're going to run it here, we're going to let's see whether I have debugging turned all the way on. Yeah, we turned debugging all the way on. So let me go back and rerun it. And let's ratchet back on the debugging to make it clear. So we turn off debugging, and we run it for 10 iterations. Run this thing again. And what you're going to see now is we ran with 10 cores. We ran the test flatMap method, and it ran sequentially. And we'll prove ourselves that in a second. And then we ran test reduce concat, which ran in parallel. But perhaps more interestingly, you can really see the difference because test reduce concat executed in 27 milliseconds, whereas test flatMap executed in 908 milliseconds. So much, much slower because it was running sequentially. In fact, it's almost a linear speed up in the number of cores. Not quite, but along those same lines. So now let's go back. Now that we kind of know the big picture view, let's go back and enable debugging. So we make that be true instead of false. And now when we run the test, we're going to get some output. And this will tell us, literally show us what is going on here. So the first thing we're going to do is the test flatMap call. You can see that for each iteration, there is a different thread ID. And that's because I've got 10 cores, so we have 10 threads. And so as a result, we got threads galore. And they're all running in parallel. But because this is the flatMap test method, if you look at what's happening inside of that print statement that we were checking to see if it was running sequentially, you'll see that there's always only one element in the map, and the element is the same as the outer thread. So what that's saying is that the inner thread is the same as the outer thread, and this is the number of requests that were processed in that particular thread. And if you take a look here, you can see iteration 1 was in thread 18. Thread 18 had one element, because that was the first one. And then thread 15, which is iteration 2, that has 2 elements. Thread 12, which was the third iteration, has 3 elements, and so on. So this whole thing is running sequentially. Now let's come down here and look at the results for test reduce concat. Again, we get a nice mapping to outer thread IDs for different threads, because we got lots of cores. But now we've got different behaviors. So you can see here that, for example, this is a really good example. Thread 18, in this case, which was iteration 8, it has several threads. So thread 18 and thread 20. So thread 20 was also running. And down here, you can see for thread 19, thread 16 and thread 20 were running. These were all running in parallel, indicating that there's parallel execution going on, because the inner thread was not the same as the outer thread. Now, there are a couple cases where, for the luck of the draw, for example, the very first iteration, the inner thread and the outer thread were the same. So that one ran, quote, sequentially. But all this other stuff, for the most part, is running in parallel. And because the way we've set up the use of the terminal operation, as long as something is running in parallel, we consider the whole thing to be running in parallel, because it is. So that's the output. It's really cool. A lot of fun putting this together. So now that we've kind of talked about what the output looks like, you can go back here and sort of see what's going on. Check inner stream thread IDs is returning either 0, 1, or 2. We filter out anything that's equal to 0 or less than, or not greater than the S intermediate result, which is 0. And then if you look up here, you can see what we're doing is we're taking the results that are coming back from these stream operations, and then we're using the all match terminal operation, which is a short circuiting operation. So for this variant, for the one that runs flatMap, all match will go through every item because they're all going to be sequential, so it has to look at them all. But down here, for the parallel version, the first time it finds one that's not sequential, it stops because that one was running in parallel. So anyway, that's the example that illustrates various things, the most important of which is that flatMap does not work in parallel when you're using it with a parallel stream. But the remedy for this is to use map in combination with the reduce and Stream.concat method.